Welcome back to Kinesthetic Knowledge on Record. I'm your host, Isha, and on today's short episode, we will be discussing sarcopenia. You're likely familiar with the concept of aging and its effects on the body. However, one aspect that doesn't often receive attention but is crucial to our overall health and well-being is the gradual loss of muscle mass and function, which is known as sarcopenia. Sarcopenia is not just a normal part of aging, but involves a complex pathophysiological changes that impact our muscles at the molecular, cellular, and systemic levels. Understanding these underlying mechanisms is essential for grasping the full scope of sarcopenia and its implications for our health. So in this episode, we will delve into the bulk of my research, which is the intricate world of sarcopenia's pathophysiology, exploring the molecular mechanisms, neuromuscular changes, metabolic factors, and more that contribute to the development and progression of this condition. It is recommended that you watch previous episodes on muscle strength and stability, as well as regeneration, as this video will build on these topics. So let's get started. It's important to understand that as we grow older, our muscles undergo changes that are part of the natural aging process. Aging affects our muscles in various ways, from structural changes to functional decline. In the case of sarcopenia, these changes actually occur a lot more quickly. Sarcopenia is actually defined as a progressive and generalized skeletal muscle disorder that involves the accelerated loss of muscle mass and function. So apart from aging, research has identified many frequent underlying causes of sarcopenia, which includes nutritional losses such as low protein and energy intake, micronutrient deficiency, malabsorption, and anorexia. It's also been shown to be associated with inactivity. So that includes bed rest and low activity. If you listened in on the episodes on quadricep weakness, you would know the implications of muscle disuse, and this is also kind of present within sarcopenia as well. We also found a lot of comorbidities that were associated with sarcopenia, and that includes bone and joint disease, cardiorespiratory disorders, metabolic disorders, endocrine diseases, particularly androgen deprivation, and neurological disorders. So the causes are quite varied and they're not really well understood. For my research in particular, I was really interested in learning the pathophysiology and how this muscle weakness came to be. So what I found really is that the process of aging disturbs the homeostasis of skeletal muscles. If you watch any of the other videos in these series by me, you would know by now that skeletal muscle requires a very intricate balance between hypertrophy and regeneration. This balance is not really well understood, and it's still a topic of heavy research. However, I did decide to explore it further. And what I found is that there appears to be an imbalance between muscle anabolic and catabolic pathways, which leads to the overall loss of skeletal muscles. There are cellular changes in sarcopenic muscles, which include reductions in the size and number of myofibers, particularly affecting the type 2 or fast twitch fibers. Now, this is something that I wasn't really surprised with, but it does make sense to find that as you age, there is a transition of muscle fibers from type 2 to type 1 fibers. There's also an increased intramuscular and intramuscular fat infiltration, or what's known as myosteatosis, and a decreased number of type 2 fiber satellite cells. So in the muscle regeneration video, I actually explained how skeletal muscles are susceptible to damage from overload and trauma, but they also have a very notable way of regenerating themselves. Satellite cells, known as the skeletal muscle specific somatic stem cells, actually play a very prominent role in muscle regeneration. So damaged myofibers are actually repaired and regenerated by satellite cells. So what does aging do? So aging causes a loss of function of these cells and thereby causing a decrease in the regenerative capacity of myofibers and a decrease in the number of myofibers. A lot of the studies that I actually looked through also found that factors that maintain this whole system were also altered as one ages. So for example, I talked about the Notch signaling. So as one ages, expression of the Notch ligand is actually decreased in the dormant muscle satellite cells, which may be involved in the decreased proliferative potential of satellite cells. In addition, it's also been reported that the Wnt signaling pathway is also enhanced with dormant satellite cells, which promote their differentiation into fibrogenic cells. Another concept which I found really interesting was to see how the NMJ, or the neuromuscular junction, also experiences great morphological changes with age. As I mentioned in the first video, the NMJ has a lot of plasticity. With age, there are morphological changes in those synapses, which result in the functional decline of the skeletal muscles and muscle atrophy overall. Outside of these mechanisms, I also explored many other potential causes of sarcopenia, and one of the first ones that I found was that in the case of myofiber atrophy and hypertrophy, a lot of it actually depends on the protein content itself. And I was actually really surprised to find that 80% of the muscles are actually composed of proteins. So the balance between muscle hypertrophy and muscle atrophy is closely tied to the protein content within the muscle fibers themselves. Muscle hypertrophy occurs when muscle protein synthesis is increased and degradation is inhibited. The opposite is true with atrophy, so in this case, degradation will increase and synthesis of proteins will be inhibited. In particular, amino acids play a really important role in this process of growth, especially the ones with branches such as leucine. Insulin and insulin-like growth factor 1, IGF-1, also contribute to muscle growth, but all of these factors are known to induce phosphorylation of a protein called mammalian target of rapamycin, or mTOR, in muscle cells. This activation actually leads to an increased protein synthesis through the activation of other proteins such as P70S6K. The mTOR complex 1 is actually a signaling pathway that stands out as a major regulator of protein metabolism. So it integrates various signals to control both protein synthesis and degradation. So going back to that example of leucine intake, as well as other things such as exercise, actually activate mTOR C1, boosting protein synthesis. Conversely, fasting inactivates this complex, leading to increased protein degradation. So what I wondered was, how does this information really fit into aging? Well, as we age, our muscles' responses to these signals change. Older adults show decreased sensitivity of mTOR C1 to leucine, which makes it a lot harder to boost protein synthesis through diet alone. Another important factor is IGF-1, which I kind of introduced early on. So that's a very potent anabolic factor, which is produced in the liver, and it plays a significant role in muscle growth and regeneration. IGF-1 actually activates pathways such as the AKT, which further activate mTOR, enhancing protein synthesis. Unfortunately, the activity of the IGF-1 and this whole system decreases with aging, contributing to that age-related muscle loss known as sarcopenia. Another key protein that I found to show up a lot in my research was ubiquitin, which is involved in tagging other proteins for degradation. When a protein is ubiquinated, it can actually be degraded by a proteasome, and this is something that we learned in our first year and as well as second year anatomy. So muscle-specific ubiquitin ligase genes such as the MURF1 and the atrogen-1 are key players in muscle degradation. These genes are upregulated in various conditions, which basically lead to muscle atrophy. So those conditions would be disuse or nerve damage. Interestingly, the levels of muscle atrophy-related factors increase in the muscles of elderly individuals, and this has been found in aging rats as well. This actually contributes to the decreased muscle synthesis and anabolic resistance, which is seen in older adults, even when the amino acid levels, like I mentioned early on, remain constant in the blood. So alongside those direct mechanisms, I found that the intricate balance between muscle protein synthesis and degradation also plays a big role in developing strategies to combat that intensified loss of muscle mass with aging. Another interesting connection I found was with the immune system. As we age, our immune function naturally declines, making elderly individuals more susceptible to chronic inflammation. This persistent low-grade inflammation process increases the risk of developing inflammatory diseases such as infection and collagen diseases. Chronic inflammation in older adults is often characterized by elevated levels of pro-inflammatory cytokines, which includes TNF alpha, interleukin 1 beta, IL-6, IL-18, and many more. So studies have shown that these pro-inflammatory cytokines can increase 2 to 4 times in elderly compared to healthy young adults. And these inflammatory cytokines have actually been shown to impair mitochondrial function, which reduces ATP production and thereby increases the production of reactive oxygen species, or ROS. Excessive ROS production further damages mitochondria and then triggers the ubiquitin proteasome system that I mentioned early on, which was the major pathway for protein degradation. This leads to skeletal muscle atrophy, where proteins tagged with ubiquitin are further broken down by the proteasome. Another factor at play is apoptosis, or what's known as the cell death mechanism. Activation of capsases by TNF-alpha leads to the rapid degradation of intracellular proteins, which are then phagocytosed by macrophages. Excessive apoptosis in skeletal muscle further accelerates protein degradation, contributing to muscle atrophy. So those were definitely some new interesting connections that I found. Another interesting connection I found was actually linked to obesity, which is a significant factor in chronic inflammation. So adipose tissue interacts with immune cells such as macrophages and neutrophils, and it induces chronic inflammation in obese individuals. Macrophages secrete TNF-alpha, which promotes lipolysis in adipose tissue through the toll-like receptor 4 signaling pathway. This leads to an increased free fatty acids and further secretion of pro-inflammatory cytokines, intensifying chronic inflammation. What I found interesting was that immune cell infiltration associated with this inflammation was not just limited to adipose tissue. There were some studies that were observed increased infiltration of macrophages into skeletal muscles as well, especially in critically ill patients aged 50 and above, which led to further muscle atrophy. So what does this all kind of mean for elderly individuals? Chronic inflammation induced by various factors, and that could be aging or even obesity, can reduce muscle strength and function by increasing macrophage infiltration into the skeletal muscle, decreasing muscle mass and promoting ectopic fat accumulation. Recently, a condition called sarcopenic obesity has been gathering a lot of attention in the scientific literature. This condition combines both muscle loss by sarcopenia and obesity. Patients with sarcopenic obesity tend to have poor prognosis compared to those with the disorders alone. So it was interesting to see how chronic inflammation plays such a crucial role in accelerating muscle loss and impairing function. Another prominent pathway that I explored was myokines. So myokines are biologically active substances produced by muscle cells, and they play a crucial role in various physiological processes. Representative myokines include IGF-1, IL-6, FGF2, and many more. So myokines can act in different ways. Some act endocrinologically on organs throughout the body, like the pancreas and brain, while others act paracrine or autocrine within the skeletal muscle itself. So a lot of the studies I explored found that when muscle fibers are damaged, myokines act as messengers in the process of muscle regeneration by the satellite cells themselves. Growth factors like IGF-1 are released and play a huge role in regulating the proliferation and differentiation of satellite cells. So IL-6, the oldest known myokine, has physiological effects that include systemic metabolic regulation. HGF activates satellite cells and the mTOR signaling pathway, which I talked about earlier on, while FGF2 regulates cell proliferation and differentiation through the MAP kinase pathway. Another prominent myokine is IL-15, which is abundantly expressed in skeletal muscles and acts endocrinologically on adipose tissues. So it actually has anabolic effects and is involved in the skeletal muscle hypertrophy, which is independent of IGF-1. When the skeletal muscle cells are treated with IL-15, protein synthesis increases and protein degradation is inhibited, which leads to further muscle fiber hypertrophy. Now, if we shift our focus to myostatin, which is a myokine belonging to another family of TGF, myostatin regulates muscle mass by inhibiting skeletal muscle differentiation. So studies which really focus on myostatin gene knockout mice showed a significant increase in muscle mass. Myostatin binds to specific receptors and suppresses the expression of genes involved in muscle differentiation, and it also inhibits different signaling pathways. And then lastly was a connection I did not think I would find, and that connection was with the renin-angiotensin system, or RAS. I found this connection quite late into my research, and I kind of wish that I connected with individuals in the class doing kidneys, but unfortunately I was unable to due to logistics. So I found a landmark report which was published in 2002, which revealed the continuous treatment with angiotensin converting enzyme, or ACE inhibitors, could basically suppress declines in knee extensor strength and walking speed. This finding actually brought attention within the scientific world to the potential role of RAS in muscle health. So RAS activation is believed to contribute to sarcopenia through two main pathways. Indirect effects, so that could be angiotensin 2 induced decreases in anabolic hormones, which includes cytokines, pro-inflammatory cytokines, and increased muscle protein degradation via elevated myostatin levels, which I mentioned earlier on, or direct oxidative stress via angiotensin 2 type 1 receptors. I just found this interesting because it does show potential for an approach to preventing sarcopenia, which is suppressing RAS activity, and it may actually offer a promising approach to preventing sarcopenia overall, but I did not find a lot of literature that was going further into it. And then finally, I also found a big connection with reproductive hormone changes. So hormones, especially sex hormones, change quite a bit during aging, so I wasn't really surprised to find this connection. There was a cross-sectional study that was done with men aged 24 to 90, and what it found was that serum testosterone levels were positively associated with skeletal muscle mass and muscle strength. This decline in testosterone levels with aging is linked to geriatric diseases and functional disabilities. Now, in contrast, when you looked at women, particularly postmenopausal women, the decline in estrogen levels can lead to endocrine and metabolic dysfunctions, which increases the risk of osteoporosis, metabolic syndrome, and sarcopenia. So the combination of osteoporosis and sarcopenia, known as osteosarcopenia, further elevates that risk of frailty that's found in older adults, which I found quite interesting to explore. So that was kind of all the main different connections that I found as I explored sarcopenia within my research and looked at muscle loss and aging. I think, although I mentioned a lot of different and complex connections, I think if there was one lesson that kept showing up, it was the complexity of this intricate balance that's found in skeletal muscles. I have mentioned this in probably every video that I've done, but I think that's probably the biggest takeaway that I would take with me as I go forward. I was really surprised to find that sarcopenia is not just an age-related problem, but it's also associated with a range of different long-term conditions. There are so many pathogenic relationships, such as the one between adipose tissue and as well as molecular changes and interlinked pathways involved, which I kind of did go over. When I first started my research into sarcopenia, I found that there was a lot of disagreement on the definition of sarcopenia, and I couldn't really see why. It seemed like a pretty straightforward condition. However, after exploring all these connections and all these potential mechanisms that kind of contribute to that disease, I understand why there's so much disagreement. I hope that the listeners took away something from this podcast. And that is all I have for today for kinesthetic knowledge on record. I will see you next time.